We will continue to go over the introduction chapter, and then today also we will start a new chapter which is on thermal energy. So last time we have started the introduction chapter and we stopped on the slide on global warming. So global warming is an effect that is not desired, okay, and is produced mainly by CO2 and methane, neon, and other gases, okay. So, and this, a lot of these gases are produced by combustion of fuels. This is why we want to reduce emissions from combustion in order to avoid global warming effect. So since the industrial, just 1 minute, let me share with you the screen. So do you see the PowerPoint now?
Yes.
Okay. So since the Industrial Revolution, there has been a sharp increase in CO2 emission associated with the burning of fossil fuels. And as you know, one of the main products of combustion is CO2. Now, CO2, water vapor, and methane are the main greenhouse gases in the atmosphere. And these gases trap infrared radiation from both the sun and the earth. And this will lead to an increase in surface temperature. Now we will explain in detail how this will take place. So because these gases trap infrared radiation, they will lead to the increase of temperature of the Earth. So, and this increase in temperature can cause climate change and can be very harmful if we reach very high temperatures of the Earth. So, in general, it can cause a good effect when we don't have excess of these gases, because already the atmosphere contains a certain proportion of these gases, and it allows to ensure a comfortable temperature at the Earth. But if the percentage of these gases increase a lot in the atmosphere, then we will have a high rise in temperature. So we can reach very high temperature at Earth, which will lead to climate change and non-desired. Sorry? Did anyone ask a question?
No.
Please can you...
بس كنت عم طفي my mic.
Okay, can you please mute your microphones to not have problems in sound? And whenever you want to ask a question, you can put them on. Okay? So, in general, due to the global warming effect, the global temperature is increasing by 0.6 with plus or minus 0.2 degrees in the 20th century. And if we continue to have this rise, we might reach very high temperature in 2100, which is not desired. So from now, we should think about strategies to reduce CO2 emissions in order to avoid the climate change and greenhouse effect. Now, when we say the business as usual scenario, this means that if we continue to produce CO2 in the same way, this will result in an approximate concentration of CO2 between 600 and 800 parts per million by volume. This means that for each million particles in the air, we will have between 600 and 800 particles of CO2. And this will result in a temperature increase by 3 to 4 degrees by 2100. And this has a very bad impact on the Earth, because this will cause ocean current and sea level rise, in addition to extreme weather condition probability. And this will affect the food production, water availability, and biodiversity. This is why we should limit the rise to 2 degrees corresponding to a CO2 concentration level of 450 particle per million per volume, which would reduce the bad effect of greenhouse gas. So we need to start thinking about what are the strategies we need to do in order to reduce CO2 emission, and if possible, to cancel them, and how we can decarbonize our air, or how we can reduce the emission of CO2 in combustion. So one of the possible research you can do is how to decarbonize air with high levels of CO2. Knowing that now 80% of our energy comes from fossil fuels, so this percentage is very large and should be decreased a lot in order to reach the expected level of CO2 desired. From here, the need for fuel switching to lower carbon intensive technology. So first we will move from coal to gas, because it will lead to lower emissions of CO2, and then we will go to renewable energy, which is it will first it's cheap, and it will be always available. In addition, that it will not produce CO2. Okay, so this is one of the main purposes that we will work on in this course. Now, reducing global warming is a demand for energy without denying the benefits that are associated with it. So we should reduce CO2 emission, but not at the extent of reducing the energy consumption. So we should go to energy strategies that will not lead to CO2 consumption. Now, currently, buildings account for 30% of energy-related global CO2 emissions, and transportation account for 20% of energy-related emissions. This is why, for example, we were trying in transportation to rely on, let's say, electric vehicles or vehicles that can work using free energy. Okay, energy conservation and energy saving resulting from behavioral changes are also possible. So we will try to reduce, let's say, use public transport instead of each person is driving his own car. We try to reduce the energy consumption as much as possible by turning light and water when not needed. So these are minimum measures that we can start from in order to reduce the CO2 emissions. So there is like an international commitment and agreement between countries that there is an urgent need to do a global issue in order to reduce CO2 emissions. Now, in order to understand better global warming effects, okay, we will see a small video together. Okay, so here, in order first to understand global warming effects, okay, we need to know that the sun emits energy in the form of light, okay, and this light is emitted through electromagnetic radiation ranging from infrared to ultraviolet waves, okay. So if we see the spectrum of the sun, this is the spectrum of light delivered by the sun. And this energy delivered by the sun is transmitted through these waves, okay? And we have a high range of wavelengths from nearly 100 nanometers to 1 millimeter, okay? We have that waves between 100 nanometers and 400 nanometers correspond to ultraviolet, and we have the visible light waves between 400 nanometers and 700 nanometers, and finally we have for waves between 700 nanometers and 1 millimeter, we have the infrared radiation. And it's very important to know the spectrum, because we will see that we have the high energy waves are ultraviolet waves, while the lower energy waves are infrared waves. Okay? And when the waves first will reach the Earth, they have a very high energy. They are the majority of them are ultraviolet waves. Okay. However, when they will strike the Earth, their energy will be reduced. Okay. So they will be reflected as infrared radiation. And if this radiation is not allowed to escape the atmosphere, it can be of high danger. Okay. Because the CO2 and the greenhouse gases have the effect that they block infrared radiation. So if we have high percentages of CO2 and the greenhouse gases in the atmosphere, they will block the reflection of infrared radiation, and this will lead to, if you want, accumulation of heat around the Earth. Okay, so now to see this, we will look at the composition first of the atmosphere. So nearly, if we consider the atmosphere, we have 78% of nitrogen, 21% of oxygen, 0.9% of argon, and all remaining gases, okay, are called the tracer gases. And one of the most important tracer gases are CO2, neon, okay? And these gases contribute to the global warming effect because they trap infrared radiation. This is why we should not exceed the percentage that is in normal balance in the atmosphere. So in general, the sum of all tracer gas percentage should be lower than 0.1%. Okay, so here you can see the variable tracer gases, and 3 of them mainly are trap infrared radiation, which are methane, CO2, okay, and nitrous oxide. So if we want to illustrate how they will play this effect, we can look here at the following example. So let us consider, for example, it's like a window, okay? Imagine that you have a window that will allow high waves. So first, ultraviolet waves will, with high energy, will penetrate into the space. And let's say inside this space, they will lose part of their energy, so they will be reflected as infrared rays. So if you have blocking effect, so if you have, for example, in your window, elements like CO2 that will trap infrared radiation, what will take place is that your inner space temperature will be much higher than you want. Okay, so this is the effect that we don't want to have. We don't want that CO2 tracer gases and other CO2 and other greenhouse gases trap the infrared radiation and emit it back to the Earth, because this will cause a very large rise in temperature. So this is why the percentage of CO2 and greenhouse gases in the atmosphere should be always controlled to avoid the bad impacts as climate change, and you will have ice melting and all the negative effects we have seen before. Okay, but it's to be mentioned also that despite the negative effect of CO2, CO2 also is very important for the life on Earth, because it's used for plants and for animals. Okay, so it's very important to have it, but not in a high proportion. So mainly, this is the introductory chapter, okay? And now, from now on, we will go in details we will take some concepts in each chapter and go in depth for each of the important elements that were introduced in this chapter. Okay, so now I will start a new chapter, which is chapter 2. Okay, in this chapter here, we will introduce thermal energy. And thermal energy is very important to understand in order to continue with the several strategies that can be used in order to convert from one type of energy to the other. Okay, so in the introduction chapter, we have seen that the main purpose of this course is to know how to convert from one type of energy to another type. This is why we should go over the different types of energy and see how they can be converted from one mode to the other. So to start by, energy is defined as the capacity of a physical system to perform work, and energy exists in several forms, such as heat energy, kinetic or mechanical energy. It can be in form of light, as we have seen for the electromagnetic waves. We have energy in the form of potential, electrical. We can have in the form of chemical or magnetic energy, as we have seen in the introduction. Now, thermal energy is one of the possible forms of energy, and it is associated with the motion of atoms, molecules, or other particles from which the body is composed. This is why we can say, in other words, that thermal energy is the total kinetic energy of the structural element of the substance. Okay? Do you see well the information in the slide, or you want me to enlarge the scale?
It's good.
Okay. So to start with, temperature is a characteristic of the thermal energy of a body due to the internal motion of molecules. So higher is the motion level of the molecules, higher will be the temperature of your body. Now, two bodies in mutual thermal contact are said to be in thermal equilibrium if they are both at the same temperature. Okay? And one of the main laws of thermodynamics is the zeros law of thermodynamics. It states that if two bodies are in equilibrium, okay, or if I have the body A and body B in thermal equilibrium, and body B and C in thermal equilibrium, then A and C will also be in thermal equilibrium, and all will have the same temperature. Okay, so if we have two bodies at same temperature, they cannot exchange heat between each other, so they will be in pure thermal equilibrium. Now, in general, the only exception is when a material changes in phase. Okay, in general, when we have heat transfer, the temperature of the material will increase as it will absorb heat. But for the only exception of phase change, and we will see in detail how to do the calculation for both cases. In case you have a phase change, your material can absorb heat, but will maintain a constant temperature. How can we understand this? We can say that when we supply heat, okay, if the temperature increases, this means that we are giving the energy in which form? In which form do you think we deliver energy when temperature will increase?
Sensible energy, sensible heat?
Yes, sensible heat, and the energy is in the form of kinetic energy. Because when you provide sensible heat, it will be, the result will be that you will have more motion of your particles. So you are giving them energy in the kinetic form. While when you have a phase change, okay, the energy you are providing will not be in the form of a kinetic energy, because it will not lead to motion of your particles. It will do something else. Do you have an idea when there is a phase change, what will happen? For example, when I go from solid to liquid,
Will that be the latent heat?
It is the latent heat, but it is absorbing the energy in which form, if not kinetic energy?
Potential.
Potential energy. What do we mean by this? Because imagine when you have, let's say, two particles. So you know that for solids, particles are very close to each other. Okay? So here, during phase change, what you do is that you provide energy in order to destroy the bonds between your molecules. Okay? And when destroying these bonds, you are giving, you are transforming your energy in a potential energy. And this potential energy will be used to separate your particles. Okay? So this is why we can explain that in phase change, we don't have increase in temperature because the energy is transformed in another way. It's transformed into potential energy able of destroying bonds, for example, when we go from solid to liquid. And when we go from liquid to gas, let's say, it will help us into separating more the particles. Now, how to calculate sensible heat, as you said? So when we have temperature change, this is called sensible heating, okay? Or it's so we have a change in temperature, while when we have a phase change, it's called latent heat, okay? So in case of sensible heating, in order to calculate the amount of heat provided, okay? So for example, I can tell you I have a container of water and I want to raise its temperature, let's say, by 10 degrees, okay? What is the heat that I should provide? In order to calculate the heat needed to go from one temperature to the other, you will use the following formula. The heat provided is equal to the mass of the material that I want to heat, and let us put units. So first for heat, it is in joule. The mass that I want to heat in kilogram. We multiply by a property called the specific heat. What is the definition of specific heat? Specific heat is the energy needed to raise the temperature, let's say, of 1 kilogram to 1 degree. Okay, so if I want to raise the temperature, if I want to raise a mass of 1 kilogram by a temperature difference of 1 degree, the energy needed is the specific heat. Okay, this is why the specific heat unit is joule per kilogram per degree. Okay, now you can have several units. So let's say instead of per degrees, you can have Kelvin or you can have Fahrenheit. Okay, so in case here you use Kelvin or Fahrenheit, then you should update delta T. Okay, so delta T is the temperature variation, the rise in temperature, or it can be a decrease in temperature. If I want to decrease the temperature, then my water or any material will release heat. And if I want to increase its temperature, I should provide heat. So Q is MC delta T. Now, since I used for the specific heat the unit of degrees, then in this case, delta T should be in degrees. Okay. If I use Fahrenheit for specific heat, so joule, let's say joule per kilogram per Fahrenheit, then delta T should be in Fahrenheit. So at the end, my Q will be in joule. Okay. Now it's to be noted that delta T in Kelvin is the same as delta T in degrees. Why? Because by definition, you have that one Kelvin, okay, is equal to the temperature in degrees, okay, plus 273. Since the difference between them is a constant, so when you have delta T, when you have a difference, okay, delta will be the same between the two. This is not the case, for example, if you are considering Fahrenheit, because you don't have a constant difference between Fahrenheit and degrees. Okay, so if you have C in joule per kilogram per degrees, You can use for delta T or delta T in degrees or delta T in Kelvin. It doesn't matter. However, if you have the specific heat joule per kilogram per Fahrenheit, then delta T should be in Fahrenheit. Okay. Now, if you want to define the heat required per unit mass, okay. So if you want to define it per unit mass, this means that you will give it in joule per kilogram, and then you don't need to have M. Okay. So if you define heat per unit mass, then it will be, let's say, small q in joule per kilogram. It will be defined only as C times delta T. Okay. So it's like you are dividing big Q by the mass M. Okay, yes, sure. From now on, I will post the slides before the session, Paul. Okay, so you can take notes. Okay. Now, in case, of course, you can use this formula in several different systems of units. So you can use it in SI units, you can use it in English units, okay? So whatever is your system of your units, this equation is valid. And for example, another